Okay, so last section we're going to look at. Okay, this section, it's very like concrete kind of stuff. Okay, it's like questions like if you took the letters A, B, C, D, how many different ways can you arrange them? So it's very like tangible kind of problems. It's not really abstract. So if you want to get into probability, which is chapter 12, which we're not going to get to, but if we were going to start some stuff after this, in order to do probability, you have to know how many ways you can do something. Like if I said, you have 3 green balls, 2 red ones, and 4 yellow ones in a bag. And I wanted to know, what are the chances that you pick a green one out followed by a red one? Or whatever colors I said. Well, to figure out the chances of that happening, the first thing you have to know is how many ways is it possible to pick a green one? Are there like 4 different outcomes that would give you a green one? 5? I mean, you have to know how many ways to count things. Okay, so that's what we're going to look at today, counting. Counting is pretty easy if you have a small number of ways to do something. Counting can get a lot harder when it gets more complicated. Like if I said to you, how many different ways can you get a full house out of 5 card hand? That's a little more complicated. Okay, first you have to figure out how many different 5-card hands are there. That's like your total. And then find out how many are the actual ones you want. Like what event, in that case, a full house. Right? So counting, it can get a little bit harder. Okay, so the idea is you're finding out how many ways can you do something. Okay. When you're counting the number of ways that something can be done, sometimes order is important, sometimes it isn't. It depends. If you were asking a question about like a combination lock or like a password, right, to something, you had like digits you typed in, do you think order would be important when you're typing in digits on a keypad? Yeah. 1, 2, 3, 4 is not the same as 4, 3, 2, 1. That's a different order, different password. But sometimes order doesn't matter. Like if I said, I want to pick a group of 4 people to have a committee. No specific roles on the committee. Everyone is just a committee member. Well, a committee member of, like, you know, Joe, Sarah, Bill, and Tom is the same as John, Bill, Sarah, Joe, whatever I said. Okay, the order that, yeah, I would have. The order that you name people in a committee, that's not important. Okay, the fact that it's just a committee, that's all you need to know. All right, so I want to take a look at this question. Using the letters A, B, C, D, how many 3-letter codes can be formed? So what do you think there? Order, important or not important? Important. Some people say important, some people... All right, so what do we think? Order, important here or not important? Not important? So if I'm telling you I'm thinking of a code, if you get the code right, like if you say ABC, that's the same as DCA. It's important, right? When you're writing a code for something, the order that you list things in, think of it like a password. Just because you know the letters of a password, that may narrow down how many options there are. But even if I tell you all the letters to my password, you still don't know the password. You have to put them in the right order. So this isn't bad. So let's go through and see if we can actually list out all the possibilities. Now, listing them out was not the question here. The question is how many different ways can you do it? Listing them is one way to then count how many. Now, if I said, all right, I'm going to give you 10 letters to pick from, how many ways could you make 3-letter passwords? I want a better way. Okay, listing out every combination, that's going to take a while. So when we list them, we just try to start with, like, kind of do it mechanically. So take any 3 letters, and let's arrange those 3 letters all the different ways. So let's start with ABC. ABC. And then I would probably do, like, A, C, B. Okay, I'm basically kind of doing it in alphabetical order. That's what I'm trying to go for. So ABC, A, C, B. We could do BAC, BCA. And then I could do what? CAB, CBA. Are there any combinations that I missed arranging those three letters? I don't think so. All right. So the idea is now I could do this a little quicker. I'd say, all right, it looks like if I pick any three letters, I can arrange them 6 ways. So rather than listing out other columns, all I have to do is figure out how many ways can you pick 3 out of 4. And that would tell you how many columns you would have. Guesses? Yeah? Okay, let me ask the question a different way. How many ways, if you have 4 things, can you leave 1 out? Yeah?
3.
You can leave 1 out. All right, if I'm picking A, B, C, D, I could choose to leave out which letter? D. Okay, there's 1. What else could I leave out? Right, 4. So asking how many ways can you leave 1 out, or how many ways can you choose and take 3 of them, that's the same question. So the next grouping I could do, but I'm not going to go through the whole thing. I could do the A, the B, and the C. So I left out D. So D, I'm just going to write that above. That's the one I left out. Here, I left out C. I could leave out B, or I could leave out A. And for each one of those, I could make 6 different arrangements. So how many different ways can you form a 3-letter code using 4 letters? Yep, there's 24. Now, we were kind of efficient about it. Like, we figured out, okay, if you take 3, any 3 can be arranged 6. How many ways can you pick 3? 4 different ways. 6 times 4, 24. So, kind of, but eventually we're going to have an even better way where you don't have to make a list at all. Okay. So, any questions on how we figured that out? Didn't really use any math, just kind of, brute force, just kind of figured it out. So, another way you can figure out how many possibilities you have is to kind of make a diagram. Kind of draw it out, thinking of it as like a choice. Like you can choose this or choose that, and then do it that way. So this says that an animal is going to perform 2 tasks. For each task that it performs, so it's going to perform a task, it can get 1 of 3 rewards. Then it's going to perform another task and get 1 of 3 rewards. So I want to know how many sequences of rewards are there. Okay, now let's do this one 2 ways. Let's do it where you can get the same reward twice in a row. So like you can choose like the candy bar the first task and the candy bar the second task. And then we'll make it so that if you choose that reward the first time, you can't choose it again the second time. So I'm just going to erase this for a second. Let's do it this way. So it doesn't really matter what the tasks are called. Let's just call it T sub 1, task 1. Now, if the animal performs that task, how many choices of rewards do they have? 3. So they could either choose reward 1, they could choose reward 2, or they could choose reward 3. Now, they're going to perform a second task. No matter which reward they pick the first time, they're going to do a task again. So when they do the next task, let's say they pick the first reward. If they can pick the same reward again, how many choices of rewards do they have the second time? 3. After they pick reward 1, they could pick reward 1 again. pick reward 2, or they could pick reward 3. Okay. What if they pick reward 2 the first time? How many choices? 3. Reward 1, reward 2, reward 3. And what if they picked reward 3? How many choices? 3. So we got reward 1, 2, 3. So how many different sequences of rewards are there? So they have like R1, 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 R2, R1, R3. How many different sequences are there? Yeah, 9. And does the order matter? Is picking reward 1 and reward 2 a different path than picking reward 2 and reward 1? Yeah, right? That's a different, like let's say you get a reward at, I don't know, 1 o'clock and 2 o'clock. Well, if you pick this one at 1 o'clock and then pick this one at 2 o'clock, if you switch them, that's different. You're getting the rewards at, you might get R1 earlier and then get R2 later versus the way we did it here. Now, that's with repetition, or you can pick same reward twice. How many ways are there to do it if you are not allowed to have, once you pick R1, you can't pick it again? There'd be 6. Because if you pick R1, then you'd only have a choice of rewards 2 and 3. If you pick 2, you could pick 1 and 3 the second time. And if you pick 3, you could pick 1 and 2. So there's only 6 ways to do it if you're not allowed to repeat rewards. So 6, pick each reward 1 time. So maybe the rewards are like something edible and you only have 1 of each. So once they eat it, you only have 1 to give away. Okay? Any questions on that? Right, so you could also use that kind of setup, like, let's say you were buying lunch, and they had choices, right? You had a choice of 3 sandwiches, you had a choice of 4 different drinks you could pick from, and the question was, how many different lunches could you make out of that? So you could kind of pick, well, if I pick sandwich 1, I could pick drink 1. If I pick sandwich 2, I could pick drink 2. If I pick sandwich 1, I could pick drink 3. So you could just go through and figure it out. But why do you think this tree diagram, probably not always the best way to do it? Yeah?
Because it'll get like really big.
Yeah, it starts to get really big, especially if the number of choices, you're making choices over and over and over, your tree just gets huge. Right? So that's why a tree diagram isn't always practical. So, let's look at what's called the fundamental counting principle. So this basically says that if you have A ways of making the first choice, and then you have B ways of making your second choice, and C ways of making your third choice, then the number of ways you could like put all those choices together is the product of all of them. So think of the reward one with repetition. The animal had a choice of 3 rewards for the first treat, had a choice of 3 rewards for the second treat. 3 times 3 gave us 9. Now, without repetition, the animal had a choice of 3 different treats the first time, and regardless of which treat it picked the first time, there would have been 2 left the second time. 3 times 2, there's my 6. Not every single counting problem falls into this exact idea, but this is for pretty basic counting problems. Things can get a little tricky, like, all right, I gave you the letters A, B, C, D. Well, what if I gave you the letters A, B, C, D? Or you know what, actually, we'll just keep it 4. A, B, C. It's a little different now. Can you distinguish between an A and an A? No. So if I write, like if I wanted to write a 3-letter code, and I write like AAB, and say, well, what if I switch the first 2? That doesn't make a different code. So when you start having things like that repeated, you have to be a little bit more clever. We'll talk a little bit about stuff like that. It's a lot easier to like arrange letters when they're all distinct. But when they're not, then you got to adjust for that. Now the fundamental counting principle can be extended to however many choices you're making. If you're making 12 choices, as long as you know how many ways you do the first one, the second, the third, the fourth, just multiply them all together. Now, this assumes that the choices are independent, meaning when you make your first option, it doesn't really change or affect later choices. Right? So like if you said, well, if you pick sandwich 1, then based on that, you have to get either coffee or tea. Like soda's not an option if you pick sandwich 1. That now complicates things. If you can only get certain drinks when you buy certain sandwiches, now it's more complicated. So we're assuming that the choices are totally independent of each other. The word independent and dependent, that's used a lot in probability. Right? Like if you're flipping a coin, if I flip heads 20 times in a row, what are my chances of flipping heads the next time I flip the coin?
50.
Still 50-50. Doesn't matter if I flipped heads 20 times, like with a fair coin. If I flip heads 20 times, that's totally independent of my next flip. Just because I got it 20 times in a row doesn't mean I'm going to more or less have a chance of getting heads the next time. I've just been lucky. I've been getting it. That's really lucky. But okay. So that would be something that's like independent. Okay, so let's look at an example with license plates. So we're going to have license plates that are made up of 2 letters and 3 digits. No letter can repeat. No number can repeat. I want to know how many different license plates can be made. Now, this is probably in the thousands. So listing them all out, not a good idea. But what I would do is probably something like this. We have a choice of 2 letters and 3 numbers. Let's figure out how many options we have for each slot. Now we're going to assume our license plates follow this pattern. Where you put the 2 letters would change the license plate. Like if the letters are in the middle, if they're at the beginning or the end, those are different license plates. But we're going to assume that the 2 letters, well, let's assume that they're right in the beginning. Okay, let's do it that way. And then maybe we could think about, okay, once we know how many ways to do it if you put the letters in the beginning, how many ways would there be to do it if you put the letters at the end? Or, in other spots. Okay, so this will be letter, letter, number, number, number. So how many choices do I have for the first letter? Yeah?
26.
26. How many choices do I have for the second letter? 25. Doesn't matter what letter you pick, there's always going to be 25 letters left to pick. Now, how many choices do I have for my first digit? 10, right? Second digit? And the third digit? 8. Doesn't matter what digit you pick. So now multiply all that together, and that's how many ways you can make a license plate with that pattern. So we got 26 times 25 times 10 times 9 times 8. So if we follow that pattern, there's 468,000 different license plates. Now, do you think all of those license plates, like if they were really making license plates, would be usable? Well, do you think they would all be, like, do you really think if they were making license plates that there would be 468,000 that they would print and actually use them all?
Well, yeah, because there's a lot of cars on the road. But like, am I like misunderstanding the question?
Well, I'm thinking like practically. You'd need more license plates than that.
Oh, yeah, well, yeah, you're gonna need way more.
Yeah, you'd need more. But why might there be license plates out of these 468,000 that would say, no, we're not using that?
If it like says something.
So if it spells something not nice, they may not use that license plate. So you could say something like, if you don't like the word cat, so you can never have the word cat spelled, or no, we have 2 letters, not 3. So you don't like the word it. So if I said to you, you know, you can never have the word it, you can have TI. So you can have I's and T's, but they can't be in order I-T. How many license plates would that leave you with? That kind of thing comes up a lot, especially with phone numbers. Okay, if you say, well, how many different phone numbers can you make? There might be, like, some phone numbers you can't use, right? Like, you could never have, if I said, like, we're going to make up a 9, how many digits in a phone number? We got what? 4, 3, 3. You might say, well, you can pick any numbers you want. You could have 10, 10, 10, 10, 10, 10, 10. So it would just be 10 to the 10th power. Well, you can't have a prefix here of 911. That won't work.
Yeah.
So if you do 911, no matter what digits you put after it, you're calling the same person all the time, and they may not like that. So there's certain prefixes like 0. Used to be like if you press 0, you'd get like an operator. So you couldn't begin a prefix with a 0 because once you press 0, it just calls the operator. So phone numbers are a lot more restrictive. All right, things like that. So 468,000 ways if the license plate starts with 2 letters and is followed by 3 numbers. But now we could say, all right, where else could we put these 2 letters? Instead of in the first 2 spots, where else could you put them? So let's call them 1, 2, 3, 4, 5. We got them in spots 1 and 2 right now. Where else could they be?
1 and 3.
You could do 1 and 3. Yeah, you could put the letters like that. 1 and 4. Or you could put the letters in spots 1 and 5. That covers every way you could put the letters, including a 1 spot. Now, what if you did 2? Could you do 2 and 1? But we already have that. 2 and, you could do a 2 and 3. Yep. A 2 and 4. And a 2 and 5. In this particular case, it doesn't make sense to have, you can't say like 2 and 2. Because once a spot's used, you can't use it again. How about if we did a 3? 3 and 1? You already have it. How about 3 and 2? 3 and 3 doesn't make sense. How about 3 and 4? We don't have that. And 3 and 5. So that covers all the ways you could put in the 3rd spot. Now the 4th spot. You got 4 and 1, 4 and 2, 4 and 3. The only one you're missing is 4 and 5. And I think that's all the different ways you could position the 2 letters. Does anybody see anything we missed? So in theory, if there's 468,000 ways like this, you would multiply this number by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that actually means there'd be 4.68 million. If you're allowed to move the 2 letters anywhere you want. Pretty sure. Right. Counting can be tough because there's really no way to check your answer. But any questions how we got the 468,000? Or my reasoning why there'd be like 4.68 million being allowed to move the letters around? Now, if we get into letters repeating, that gets a lot harder because it would give you more options, but some things would look the same. Right? So having like an A here and an A here would be another option, but switching these two letters is not another option because they're the same letter. So that's why I said without repetition. Okay, it gets more confusing. Okay, so now we've got 8 runners in a race. How many ways can they finish? So what do you think here in terms of like order? Do you think the order matters? Yeah. All right. The order that the runners finish in matters. It's like a password. Okay? It does make a difference. So what I kind of do is I just think of it. There's the 8 runners. And think of these as the places. 1, 2, 3, 4, 5, 6, 7th, and 8th place. How many choices do you have for the first place finisher? You have 8. So if there's 8 people, you could pick any one of them and say, okay, they're coming in first. Like let's say you're trying to make a prediction. Who's going to finish first, second, third, fourth? How about the second place finisher? You have 7 choices left. And then it goes down like this. Well, what's the short way to write that?
8 factorial.
Yeah, that's an 8 factorial. Okay, so there's 8 factorial ways for the runners to finish. And that's pretty big. So 8 factorial is 40,320. So 40,320 ways that those 8 runners could finish. Okay? It's kind of like if I said, here's the letters A, B, C, D, E, F, G, H. Arrange them in every possible order you could. That's the same question. So a lot of times with counting, it kind of helps if you get confused with the question, reword the question to another question that's really the same thing. Right? Some people don't think well with like runners in a race, but they can conceptualize everything as letters and rearranging letters. Same thing. So any questions on that? All right. So, in those examples, we use the fundamental counting principle to figure out the number of arrangements. Whether we were arranging letters, numbers, or names of people. Those are all called permutations. The orders that the runner finished in a race, there were 40,000 something permutations of the order the runners could finish. There were 468,000 different permutations of license plates. The key that makes something a permutation is that the specific order matters. Right? If I ever get confused if order matters, I try to relate it to real life. So I say, okay, if I went by a cop and he knew all the letters of my license plate, but he didn't remember the order, could he somehow look up my car and give me a ticket? No. If he just knows all the letters and there's millions of combinations and he doesn't remember the order they were in, well, the order is important. Because you might have the same letters and numbers in your license plate as I do, but the order is what makes a difference. Password, right? You may use the same letters that I do for a password, but it's the ordering of those letters that makes a difference. So a permutation of a specific number of elements is called an ordering of those elements. And most of the time, we're not interested in listing all the orderings, okay? Especially when there's over 500,000 of them, like the license plates or the runners in a race. We're not interested in listing them all out. But once we know how many ways, let's go back here, like how many ways these runners could finish, then I could say to you, let's say Sarah is one of the runners in this race. I could say, what's the probability that Sarah finishes first? Right? Well, the way you do probabilities, it's how many, it's in the bottom of your fraction, it's the total number of ways something could happen. In the top of the fraction, it's the total number of ways you want it to happen. So how many ways could Sarah finish first? Well, if I was doing a problem like that, I would say, well, I have one choice for the first place position. Sarah. That's the only person I want to finish first. And then from there, I could say, well, second place, there could be 7 different people that could finish in second place. Let's say I just wanted to look at the top 2. Like how many ways could Sarah finish first, just focusing on the top 2. Right? There's basically 7 different ways she could finish first. Sarah could finish first, and then it could be Lucas, or it could be Sarah and Rob, or it could be Sarah and Jacob, or Sarah and Kim. Right? It could be Sarah and 7 other people. And then I could say, all right, so there's 7 ways she could finish first, just focusing on the top 2, divided out of 40,000, and that would give me the probability that she finishes first. Now, the thing about probability is a lot of times you're assuming every outcome is equally likely. Well, that might not be true. Like, Sarah might be a better runner than someone else, so she may have a higher chance of finishing first, and she might not have an equal chance with everybody else, right? So then you start to get into like, maybe you look at like past history, has she won races in the past? So it gets a little more complicated to kind of predict. But that's a huge part of probability. Like, okay, let's predict, like in like gambling or sports betting. All right, so we have some data about how the team's done in the past. Let's try to predict what we think is going to happen and what are the chances of it. Okay, so there's a lot of stuff with probability. So in general, if you want to say, okay, here's 12 objects, how many ways can you put them in order? The answer is 12 factorial. So if you have n elements, and you want to know how many ways you can put them in a certain order, it's n factorial. But sometimes we only want a subset of those elements. Let's go back to the runners in the race. So we've got 8 people in a race. I want to know how many different ways I can have a top 3 finish. I don't care about anything below that. Just tell me all the different ways we can have those 8 people finishing in the top 3. So we'll take a look at that. Okay. So it says we have a group of 15 people. And we're going to pick different roles. Okay. All right, so think of it as like you've got a pool of 15 people to pick from. And out of those 15 people, you want to give out the position of president, vice president, secretary, and... Oh, there's 3, okay. So we're picking 3. So think of each position, like here's president, vice president, secretary, or whatever they are. President, yeah. Start with the president. How many options do you have to pick for the president? You have 15. Now, we're going to assume, I don't think it says this, but one person can only hold one role. Okay? If you're ever not sure, like on the test, you can always ask me, but assume that each person has one role. Now, you pick the president. How many options do you have for vice president? 14. And secretary? 13. So it's not 15 factorial. It's not 15 times 14 times 13 times all the way down. It's just 15 times 14 times 13. 15, 14, 13. So there's 2,730 ways to do that. Slightly different question, but exactly the same logic to figure it out. You have 15 people in a race. How many ways can you have a top 3 finish? It's exactly the same answer. Okay. Questions on that? So some people like combinatorics because it's very concrete. But the thing that's tough with this is there really isn't a good way to check your answer. And you can't list out all the possibilities and count them. It's just too many. So you can't really check it. So that last example is what you call an R permutation. An R permutation is when you're only going to try to order R elements out of n of them. In our last example, we ordered 3 elements out of 15. Now, if you order more and more elements, does that mean you get more and more options all the time? To a point. It's kind of like this halfway point. Maybe somewhere around like, if you're doing 15, around like 7 or 8, where that's going to be the maximum number of options you could get. But then as you start going more and more, the number of options starts to go back down again. Anybody remember when we saw something like that before? Where we had like a list of numbers and like the numbers went up to a certain point and then they went back down. And it was kind of symmetrical, this list.
Pascal's triangle.
In Pascal's triangle. Okay, so when we used Pascal's triangle, they went up until they got to the middle and then they went back down. And I kind of did this earlier, but I didn't really tell you I was doing it. If I have 4 objects, and I say, how many ways can I pick 3? That's exactly the same question as how many ways can you leave out 1? Same question. So sometimes it's just easier to think of the same question from like the negative view of it versus positive view. Okay. And in probability, we do that a lot. Like if it's really hard for me to figure out how many ways I can't do something, then I'll say, okay, I'll figure out how many ways I can do it and subtract that from 100. Because how many ways I can do it and how many ways I can't do it has to add up to 100% chance. It's either going to happen or it's not. So if one of those is easier, you shoot for the one that's easier and you kind of work from there. So that's the symbol for an R permutation. NPR. N is how many elements you're ordering, or how many you have to pick from. R is how many out of those you're ordering. So in the last problem we did, I think it was 15, choose 3. Now, you can use a formula to do it. N factorial over n minus r factorial. Or, okay, on the calculator, if you go to math, probability, there's an NPR there. Now, I think I have to type the 15 in before I press this, so let me press it and see what happens. Oh, actually I can do it this way. 15. And I want to pick 3 of them to order. So this is like the president, vice president, secretary. 2,730, 2,730. Okay, so that's called an R permutation. That's the notation, and this, you did that right here. 15 times 14 times 13, that's exactly what you just did. Any questions on that? Okay. Does anyone need to see this one again using the formula? People feel like they could plug in 15 for n and 3 for r and do it out? It would just be a lot of canceling. Okay, like we had last week with factorials, just a lot of stuff cancels out. Okay, how many 5-letter codes can be made using the entire alphabet? Okay, so a couple things we need to know. How many letters in the alphabet? Okay, that's kind of important. So we have a pool of 26 things to pick from. And how many of them are we picking at a time? 5. You're picking up to 5 at a time to make a code. So this is the notation. Okay, let's figure it out by hand, and then we'll use the calculator to see if we get the same thing. Okay. What goes in the top of my fraction to figure this out? 10 factorial?
And factorial.
Yes, but I know what is n here.
26.
26. What goes in the bottom? 21 factorial. So if you were to write out the entire top and the entire bottom, you'd have 26 times 25 all the way down. From what number down is everything going to cancel? Yeah, everything from 21. So all you're left with is 26, 25, 24, 23, 22. So it should be 7,893,000. Okay, let's check. So 26, choose 5. Yep. Wait a minute. 78926, 7893. Did I just not copy something down? Yeah, I just forgot to copy it. Sorry. Now, does anyone think they know what this would be the same as? You could do 20, you could say, all right, how many ways are there to pick 5 out of 26? Or think of that symmetry in the triangle, like, yeah? Yeah, I think it would be 21, unless we're one off, but let's see. 21. Hold that thought. I think I know what happened. Let me try, yes, let me try this. Don't worry what this symbol is, I'll tell you later. So let's do that, and we get that. Now let's do the same thing with a 21. Yes, that's, I was thinking of something different. The difference here, permutation, combination. So with combinations, that's where Pascal's triangle is going to come in. Okay? But don't worry about it for this. Any questions on the 7.89? All right. So, combinations. Permutation, order matters. And on the test, I'm going to ask you like 4 or 5 questions. I'm just going to give you a situation and say, combination, permutation. Just tell me, which one do you think it is? And there's no vague ones, like it's clear. It's either the order is important or the order is not. What if I told you digits to a combination lock? Does the order matter? Yeah, if I tell you here's a combination lock, the digits to the combination are in no specific order, 10, 13, 72. Well, you still have a few options to try with those numbers. Not many, only 6. All right, so with counting, we're looking at the number of ways we can make a subset from a given set of elements. All right, so the best example I usually think of is like a committee. Right? You give me 20 people to pick from, I want to make a committee of 4 people. It doesn't matter what order I pick the people in. It's not like they're going to be president, vice president, secretary, treasurer. They're just going to be a committee of 4 people all working together. So, in that case, order would not be important. If I said to you, how many ways can I take $1 and make change for it using quarters and dimes? How many different ways can I break up $1? The order there wouldn't matter. If you say, well, you could use 2 quarters and 5 dimes, or 5 dimes and 2 quarters, it's the same thing. There's still the same objects in a pile in front of me. The order of the quarters and dimes doesn't matter. Any questions on that? Okay. So, how many committees can you make where the committee is 3 people and you have 4 to pick from? So think of the people. This one we'll list it out. Here's the people, A, B, C, D. What's one committee you could make out of those 4 people? Lucas?
A, B, C.
Yep. You could have persons A, B, and C on a committee. What's another committee you could make? Yeah. B, C, D. Okay. What else? Yeah. A, B, D. Okay. Any other way we could make a committee? Yep.
A, C, D.
A, C, D. Any other way we could make a committee? No, that's it. How comes not CBA? It's the same committee. Just saying like Joe, Sarah, Tom, Tom, Sarah, Joe. It's still the same 3 people on the committee. It's not like they each have specific roles. So the answer there, 4. Now, not bad. You could list them out, but just like with anything else, sometimes it gets kind of time consuming. So the notation for this, you've seen this before. You haven't seen this, but you've seen this one. When did that, like parentheses with a number in the top and the bottom, when did that come up last week? Yeah?
Like finding a number in a sequence?
Or
not a sequence, but like a set of numbers? Like
so it was finding a number. Did anyone remember where that number came from? Right, this is a binomial coefficient. So it did come up with the coefficient in a series when we were adding things up. But when we did that earlier, we just called it a binomial coefficient. And I told you that it was pronounced 4 choose 3. And I kind of said the reason it's 4 choose 3, we'll see next week. But this is why. So 4 choose 3. N factorial over n minus r factorial, r factorial. So you already have that formula in your notes. Okay, I'm not. You'll have to check. I would know the formula. Because for this week, I think the test we're just going to use just a regular calculator. There's nothing you need to graph. There's no graphing at all. So, any questions how to figure out how I got these numbers, where they came from? Okay. I mean, yeah, factorials can get kind of big, but usually most of it cancels out anyway. All right, so we have a set of n objects, and we want to pick r of them to form a subset. Okay, so that's the formula. I've just written it out without specific numbers for a combination. And I said it earlier. N factorial over n minus r factorial, r factorial. So given like a set of items, which do you think would be bigger? A permutation of that set of items or combinations? Which one do you think would have more options? Permutations, because you can count ABC as different from CBA. Look at the combination of 4 choose 3. There was only 4. Look at the very first problem we did. A permutation of 4 choose 3. 24. Okay, so there was a lot more. So that's your formula and notation for combinations. Okay. On the test, it always surprises me when I have the section about tell me if this is a combination or permutation. People, they mix them up. Right? So just remember, permutation, the order matters. Passwords, giving people certain positions in a group. Runners finishing in a race. Cars finishing in a race. Same thing. Order is important. Okay, so a certain basketball team has 12 players. How many different groups are there for the starting 5? I'm not assigning roles to them. I'm not saying they're going to be the point guard, they're going to be the center. I'm just saying there's 5 people. I just want to know how many different groups of 5 people can I have. Now, if you start giving them roles, that's a permutation. But the way this is written, combination. So it's a combination of, can somebody tell me how many choose how many? Yeah?
12 choose 5.
Yeah. So now you just have to know how to figure that out. N, R. N factorial over N minus R factorial, R factorial. Now, don't bother doing all that out because most of it's going to cancel. 12 minus 5 factorial gives me what number? 7 factorial. So if I were to write out the top, everything from what number down is gone? 7. So you're going to have 12, 11, 10, 9, 8. And what's still left in the bottom? Yeah. 5, 4, 3, 2, 1. Now, when you're doing a combination or a permutation, you're never going to get what kind of answer? Fraction, right? There's not like you can do something 2.5 folds. So everything there should cancel. Sebastian, what can I cancel the 5 and 2? Yep, how many times? All right. And then I got a 2 and a 2, so I might as well just do that. How about the 4? That can go into... Yep, tell me. 12 or?
8.
Doesn't matter. So you said 12 first, so 4 goes into 12, 3, and 3's gone. So I'm left with a relatively small number. Still maybe a little bigger than I can do in my head, but 33 times 9 times 8.
Cancel the 3.
Oh yeah, I canceled that. So just 11 times 9 times 8. Thank you. So 792. Any questions on that? So that's all the test on Thursday, Wednesday will be on. Okay, combinations and permutations. Yep, that's what the test will be on. Okay, so homework, it's page 631, and it's 1 through 5. 7 through 12, 14 to 19, 21 and 23. Okay, you got about, well, a little over 20 minutes left. So please use the time, try to get started. If you have any questions, let me know. If you need a book, I got it.